welcome to CS107 Computer Systems. If that's what you're looking for, you are in the right place. If you look at this and you're a little terrified, you're in the right place, right? Like, whoa, I thought I knew code, and then there's a whole new layer to it. We are Julie Fonsky and Chris Gray. We'll tell you a little bit about ourselves in a minute, but we're the co-conspirators of this enterprise. And what we're going to do today is kind of work us through kind of a little bit of an overview of what we're on the mission together to do, some things about how the class is going to work, and then give you some demo of the tools we're going to be using, and then if we get a little chance, we can sort of just start diving in on the material and sort of move ahead with the things that we have planned for this quarter. So that's kind of the agenda for today. It's a great day to ask questions about stuff, especially you're trying to figure out if this class is right for you and kind of how it fits into your plans and things like that. And so we are totally willing and interested and able to take those questions. But just try to make it known that you have something that you need addressed, because it's a big room and it's something that's hard to see unless you kind of try to draw attention to yourself. So don't be shy about doing that. That's kind of the ground rules for today. Shall we move forward? Yeah. So tell you what, how we're going to try to work this up. We're going to kind of mix it up a little bit because I'm going to tag team because we both want to be here to welcome you. Try to give you a sense of what the class is about, deal with some of the kind of vision and philosophy, as well as some of the more mundane logistics about how it works, right? Show you our tools, right? Tell you about some kind of key elements that you're going to need to become familiar with, and we're going to kind of get introduced to, and then deal with some of the going on to show you and demo stuff as the lecture goes on. All right, so what is 107? Let's just start right there. 107, all you need to know, 107 is awesome. Now you're done. So we start with 106 A and B, which are two fabulous and awesome courses that we hope you all have a chance to experience one or both of those classes, depending on kind of where your background has led you here. And what we do with 106 A and B is, right, we have this model of trying to bring you in and get you excited about how you can harness the power of the computer to do cool things, solve all kinds of neat problems, right? And as well, kind of teach you a lot of the techniques that allow you to break down those problems and wrestle them into submission, right? So learning about cool data structures and algorithms and decomposition and debugging and all the kind of smart engineering techniques that help you to get those things done. At the end of 106B, you're a really pretty strong programmer, but your experience has been a little bit constrained to certain tools, certain languages, you know, a certain context, right, that we set up to kind of give you that, that intro experience, right? When we get to 107, our goal is to kind of take you deeper into what we call the systems core of the major. And so at this point, what we're looking at is we've got this good programming knowledge, but we want to strengthen it, we want to deepen it, and we in particular want to deepen our understanding of how the system itself works. That when we declare and manipulate an integer variable, what's really going on there, right? What is it that the hardware that underpins us, right, allows us to express with that integer and its computation? What are the, you know, what can it do for us? What can it not do for us? Are there limitations to it? Does it ever, you know, kind of, you know, give up on us? Do we need to know? How does it really work under the hood? And so there have been things definitely probably once maybe where you had, you know, something you did in your program and you changed it a little bit and it behaved in a way that was a little bit mysterious. And your section leader said to you, don't worry for that for now. You know, Julie's going to take care of you when you get to 107, right? It's like, well, there's something a little bit that's unexplained about the cause and effect between this change and that result, or you moved your program, you were running on a Mac, and then you ran on your friend's Windows machine, and it just behaved differently. And you're like, but wasn't it the same code? I'm running the same code. Why is it doing something different? It's like, oh, because the system is different, right? There are different kind of layers in there that are changing some of the outcomes. So we're going to try to understand that system. Like, we write C code, but it really is translated by the compiler into assembly code, and assembly code is what is translated then by the assembler into machine code. That's what your chip really understands. It has a very primitive heart, you know, and soul down there in the silicon, and yet we have all these abstractions we built on top that allow us to think of it as capable of these wonderful, marvelous things. But in fact, that whole system had to be architected and built and maintained and understood for you to be able to harness it to its maximum effectiveness. So that's going to be our goal, to give you this like top to bottom. You know, I know how to write code, but I also know how that code really runs at runtime, how it really behaves, what's going on with memory, what's going on with the control flow, what's going on with the hardware. That gives you this kind of complete, you know, understanding of the whole system and how it's put together. And that is super powerful understanding. Really neat and empowering and cool. You will become this kind of wizard of understanding that system. So that is our goal for you, right? Is to take you from kind of this novice sort of apprenticeship that you've done in 106 to this kind of journeyman practitioner who really has this much more complete understanding of that system and how to harness it to maximum effectiveness. So that's where we're going. So how does that translate into actual learning goals. Like this is, helpful to say, well, what are you going to be able to do at the end of 107 that maybe you're not yet ready to do now? So we're going to take you on this journey together. Where are we going? Well, you're going to become a pretty kick-ass C programmer. C turns out to be the lingua franca of all systems code. The people who really deal with the hardware, right, don't deal with high-level languages. They're not working in JavaScript and Python, and so those are nice abstractions, right? But when you need to talk to the metal, you got to talk to the metal. The metal wants to talk to you, right, at a very low level. So we're going to be seeing a lot more of that low level, up close and personal, right? How memory is directly manipulated and things like that. So you're going to become pretty. We're going to do a lot of practice with C assembly, so that's going to be a big component of where you're building the skill set. You're also going to get this kind of complete understanding, being able to figure out what tools you can use to dissect and understand and manipulate. So getting way better at the debugger, way better at Unix, which is the environment we're going to be working in. The tools that we'll have, the compilers and the debugger and the memory debugger tool, downgrade and things like that, are all going to be kind of a part of your tool set. So you're going to just build out this repertoire of new things that you know how to use and employ. And then along the way, I think you're also just building out your skill set for adapting to new environments, adapting to new tools, learning how to learn, right, and go forward at that. Whereas the 106 is everything was kind of a little bit laid out for you, right, in kind of neat little chunks, right. We're going to start building up this ability for you to become very self-sufficient and moving forward on your own, and kind of taking on new knowledge, which will be really cool. So there are things that, like, about how we learn about computer arithmetic and runtime performance and portability that are actually kind of related to, once we understand the system we have, we're better able to understand what its strengths are, what its weaknesses are, how we can make code run faster on that system, why the same code moved to another system behaves differently, what we can do about it. So all these things that just kind of build you out to be this kind of much more aware programmer about how the system is interacting with your code and your intentions in ways that you can make it do cool things. At the very bottom, I mentioned that a little exposure of computer architecture. So there are certain classes in the kind of in the intersection between CS and EE, which are really about computer architectures. It's really like understanding how you design a chip, right? And how it, is it multi-core? What kind of buses does it have? What kind of cache and things like that? That's really not our focus. So if that's actually something you're looking to do, I think you want to be looking at the EE course offerings. So this is really a software side approach to the system. So working from the hardware upwards, right, to our languages like C and seeing those pieces in between there, but not digging too far underneath that, right? So if that's so realize we'll have a little chance to touch on that, but that won't be the big focus of what we do. So that's kind of the big picture of where we're going. We're going to come back and kind of go through some things about it, but I wanted to kind of start with that because it's like important to know, hey, what are we on? What are we doing? I will tell you who I am, and I'll have Chris introduce himself too. So, and then we'll have our TAs stand, so you'll know kind of who's your guidepost in getting us through this. I am Julie Zelensky. I have been a lecturer in the department at Stanford for 25 years. Before that, I was a graduate student and an undergraduate student, so Stanford is home to me. I have been here forever, and love this place, love this class, love being a part of the journey that as we transition right from novice to journeyman. So I'm really excited to be here with you to do that. Let me have Chris.
I'll just hold this one and stick this one over there somehow. There we go. There we go. All right, so I'm Chris Gregg. Whoa, too loud, sorry. I know a lot of you guys from 106B, so it's so good to see you all. I guess you stuck around for more classes, so that's great. I am in my sophomore year here at Stanford. I just arrived last year. Before that, I actually taught at Tufts University in Massachusetts, and then before that I was in graduate school. Before that I was in the Navy for a number of years. So while Julie and I are roughly the same vintage, she has had many more years here at Stanford and has actually worked on this course very, very extensively. So Julie, I'm really excited to be working with you here. So that's the two of us. We are both co-teaching the class. You can feel free to email one or either of us for the details if you need to talk to a professor in the class, but you can also CC both of us, and one of us will probably answer you. So you'll see both of us up here doing not so much tag team every day, but we're going to be doing like individual lectures. I'll do a few, Julie will do a few, etc. So that's that. All right, so if our TAs could stand up, those of you who are here, we have a whole bunch of TAs. Give these guys a round of applause already. You guys are going to be awesome. So many of the TAs, we get to choose kind of who the TAs are for this class, and we always choose like the best and the brightest. Not to say that the other classes don't have those, but we try to get great TAs for this class because we know that this is a hard class, and we know that that they are like the people that teach you the lab and do lots and lots and lots and lots of office hours with you guys. So we want them to be very good at what they do, and they all love the systemsy kind of stuff. So that's the TA. So you'll see them very often in labs and so forth. All right, Julie, back to you.
All right, I'm back. I got logistics, boring and necessary logistics. Okay. So what do you need to know about kind of just the run-of-the-mill, what kind of things happen in this class, right? What are the structures that we're using? Yeah. So the textbook always sort of a question because our textbook is, admittedly, very expensive. Textbook marketing is sort of a little out of control in the US, right? So the book that we have chosen for the course is the Bright Howard Computer Systems book. It's really an excellent book. It's I think I really respect what went into making it, but it is an expensive thing to buy brand new. What we have in the bookstore stock is a cut down that has just the chapters that we actually cover, so it actually kind of keeps your cost down. But I do like to say that 110, the follow-on class to this, right, uses the other chapters, right? So you could end up buying 2 cut downs, right? The first half for 107 and then by the second half when you get to 110, or you might just want to buy the full edition now and kind of have the whole thing laid out for you. And the nice thing about the full book is that it's actually hardbound, whereas the cut down to kind of keep the cost down is paperback, so that makes it a little cheaper construction, but should hopefully see you through. That book, we won't assign exercises in it. It's just not like that kind of like I really need to have exactly, this thing at all times to get my work done, but it has really great background material, great reading, great exercise problems to work through for yourself, right? Diagrams and explanations, right, that just complement the things we're doing together in lecture and lab, and serve as kind of background reading getting into that material. I think it's a really valuable book, so I highly encourage you to find a way to get access to it, right? It is on reserve in the engineering library, for example, if you just want to go do the meeting there and whatnot, but I think find a way to get access to it. There are 2 prior editions to it, so we're at the 3rd edition. The prior 2 editions just won't work. There was a pretty big overhaul moving from the 32-bit to the 64-bit architectures. That means that a massive amount of the book underwent a pretty big transition. If you try to use the old book, it's going to give you a bunch of information that's really out of date. So it's got to be the 3rd edition or higher that's going to keep you informed. You will want a C reference also, something, a go-to. That doesn't need to be a book, it could be a website, it could be a friend, it could be Stack Overflow. But sometimes you're just going to be, like I need to know something about how the C language works here, right? We're not going to really try to teach you C per se. C can be a vehicle for exploring the system stuff. But you do want to say, I don't understand this compiler message, or this feature of the language, where do I go to get that, right? So we say K&R, Tony and Richie are the authors of the language, right? So they're kind of celebrated as writing a classic book, the C programming language. The book's very official. It's available via the ebooks that Safari Books Online that our library subscribes to, so you can actually just get a full electronic copy through that, not have to purchase anything, but if you have other ways to kind of bolster your, find resources to use, and all good with us, just making sure you have a go-to when it comes to C. All right. Then, what are we going to be doing? And how are we going to do it? We're going to largely work on a kind of a week-based cycle. Is kind of the rhythm of 107, where on the Friday and Monday of any given week, right, we'll be introducing a topic. So there'll be some reading ahead of time to kind of get used to it, right? There'll be a lecture on Friday and Monday that kind of delves into it. We'll do examples and work through things to you, right? Kind of into the work example model of teaching and learning. And so seeing this and experimenting with it and seeing somebody else kind of do stuff with you. Then what will happen, so the lecture thing Monday and Friday, there'll be the in-between on the Tuesday, Wednesday, Thursday, we have labs. So you'll sign up for and have a regular 2-hour lab, where then it becomes hands-on. It's like, okay, I saw this happen in lecture, but now I gotta do it for myself, right? I gotta see how this works, I gotta try some stuff, I gotta experiment, I gotta write some code, I gotta read some code, I gotta analyze and understand some stuff. And then the TAs will be the lab leaders for that, right? So working in a small group and giving you guidance as you work through those exercises. And then the kind of follow-through to that will be then the assignment that allows you to kind of just really put it all into practice. So at the end of the cycle for a given topic, right, you'll kind of have a graduated introduction to kind of work your way through it. And so we'll start at the beginning with like just integers and how data, bits, and bytes kind of represent the position in the computer was that I have zeros and ones, right? So that'll be that kind of just right away, just starting with like, okay, let's start digging under the hood and seeing how these things work, right? We move on to a bunch of C work for the next few weeks, right? Mostly focused on how C manages memory, because that's actually kind of the key feature that a low-level language like C gives us, is this direct access to memory, right? And that enables a bunch of things that a language that's a little higher level and kind of more guarded doesn't give us. We're going to find out what we can do with that once we have that kind of control. And then we'll come back and look at floating point. So that's how do we represent numbers with a fractional component, right? Which is another interesting representation issue. That's pretty much everything that comes up to the midterm, so it's all about C and data. At the midterm, right, we kind of switch gears and start digging deeper, and that's when we're starting to look at the x86, which is the ISA of the architecture we're working on, right? We're working on Intel 64-bit machines, right, running Linux, right? And so that'll be like, yeah, how does C actually turn into something that the silicon, implements, right? What's going on in terms of those instructions and control flow and how things are being moved and manipulated at that level? So really getting this understanding of what the compiler is doing, right, to enable our C-expressed things to run on the hardware. And then once we have kind of that picture together, we're ready to start trying to kind of complete out the picture of, like, well, what is the real runtime, so the compile time and runtime features of our language? We write stuff, what happens, what does the compiler do, what does the linker do, what does the loader do, what's happening at the runtime, what are the tools that we have help us to understand and model that, right? Where do we get performance benefits, where do we not, where do we run up against limitations of the hardware, like what do the caches do? So kind of having this picture of sort of how all those things integrate and work together. And then as we get to the end, we're hoping to kind of dive into kind of a bigger case study, sort of looking at some of the systems code that's out there. And really, now that we have kind of this fundamental understanding of lots of these things, like we can read that code, we can understand that code, we can look at the choices there, we can critique it and review it, and understand the choices that were made in it, and reflect on the, how we can learn from that how to write code of our own, right, that has the same kind of successful components that we're seeing, that's kind of working, professional code and things like that. So the two things that were called out, particularly on the schedule, are the exams. Just for logistic reasons, it's important to know that the exams are in class and scheduled sort of day one, so that you can put them in your calendar right now and lock it down and plan to be there. Because in a class of this size, right, there just is not flexibility about giving you exams at alternate times. We will do the necessary OAE accommodations, certainly, but other than that, right, you need to plan to be here with us at those days, on those times, right, so that we can do the assessments together in a standard fashion for everyone. So I think that's a good thing to get on your calendar as you see it right now. All of this stuff is actually on the website, so we have I put it on a handout today, which actually kind of like just little highlights of what's going on, but the website really is kind of the go-to for everything. So CS107.stanford.edu has the syllabus, and the labs, and the assignments, and the resource materials and background stuff, and information on how to use our forum, and information on how labs work. All that kind of stuff is actually kind of in great detail. So it's a good place to go kind of poke around and get an idea of what we've got there. Now, I get to give it to you.
All right. So we thought we'd give you a little bit of an intro into the C language today, which is, I'm going to sit down for this because I have to do a bit of typing. You guys have seen this exact graph, although it was an earlier version if you were in CS106B with me. This is a graph of the various programming languages, some of the various programming languages that this group that measures these things decided were the most important languages out there right now. And you'll notice something on here. The one in blue here is Java. If you took 106A, you would have studied that. The one in green down here is C++, 106B. And guess what the black one is? C, which is 107. So we're hammering you with like the most popular languages here. Now, that's not to say that other languages aren't important too. If you look at the kind of purplish one here, Python has kind of gotten, I don't know, the little minor dips don't really mean too much, but Python is really important these days. C#, which is a Windows-only language, kind of is important, but some of the other ones are super important too. But the ones that we're going to talk about in the intro classes, including 107, are the ones that are the big ones out there. So that's where we kind of start. And by the way, I think if you were in 106B with me, you would have remembered what I said was the most common language in programming. Profanity, because it's like frustrating. That's the way it goes. So C is not a new language. Like 1970 is when C was created. It's been around a while, and it got a stranglehold on systems because it was used and in fact created to produce the Unix operating system, which had a goal of being able to be rewritten for many different types of computers. And the way they did that was every computer has its own assembly language, but C is a higher level language that we were able to, that you're able to write the same code for multiple machines, and it gets compiled down to the assembly language. So we're going to look at the assembly language in this class, but that's where kind of C came from. It was meant to be a higher level portable language. So it's interesting. The nice thing about it is if you've done any C or Java programming, the syntax will look very familiar. In a minute, we're going to write a little hello world program, and you're going to go, oh, I get that. It's exactly like a C++ program. In fact, C++ is a direct descendant of C. So many of the programs can work between the two. Some of the things about C that are important. It is small. C is one language where by the end of, maybe not quite this course, but by the end of like learning about C, you can become an expert in C, right? That is not true about Java. That's not true about Java or C++. Like you can almost never become an expert. There's like two in the world, right? The people who invented the languages, right? But in C, it's a very small core to the language. Yes, there are lots of libraries, but you can understand everything there is to understand about C. And one of the things in this class that we're going to do is teach you a lot of that. So that's great. It's minimalist. I mean, it's relatively straightforward. The language itself, not that much to it, but that's where libraries and things come into play, right? Very concerned about efficiency. They wanted to make this so that you'd be able to write fast, efficient programs, and some of the downsides to that are it's not particularly safe. In 106B, you would have heard that, hey, C++ is not that safe, whereas Java is very safe. But C kind of takes it to another level. If you liked pointers in 106B, you're going to love them here because there's a ton of work we're going to do at the lowest level where the compiler can't necessarily make choices for you that are safe, and you have to do those as the programmer. So we're going to learn some of those tricks as we go along. Okay, some of the things that are going to be very familiar to you. The syntax, as I said, very similar. Basic data types, ints, doubles, floats, chars. You will have seen a lot of those. C does not actually have a bool data type, believe it or not, although you just pound include something and you can get it. But the operators are the same, right? The double ampersand for and is the same in C, that sort of thing. Plus, minus, all those things are all the same. Some things aren't missing, right? C is not an object-oriented programming language, right? You cannot overload operators. You don't get any classes, right? The libraries are relatively thin. Like they do things and they do them well, but they're not these big giant classes that do all sorts of things. There is no string, right? We'll talk about C strings, but there's no C++ string that has like a method to tell you the length of it. Doesn't exist in C. Okay, so that's going to be interesting. The compiler doesn't do quite as many checks on C because it just can't. It doesn't have the infrastructure to do that. Okay, but as I said, it's a small language, right? It's a procedural language, whereas C++ has both procedural and object-oriented parts to it, and Java is considered a very pure object-oriented language. So those are going to be some of the comparisons that you're going to see. Now, let's go and write our first Hello World program. So one of the things you're going to notice here is that I'm in the terminal. There is no more Eclipse. There is no more Qt Creator. Some of you guys are saying, yay! But we're going to be using the terminal. Your first assignment 0, which is due on Friday, is going... Oh, it's due next Monday. I lied, sorry. Due next Monday, is going to be all about learning how to use the terminal that I'm going to show you here in a second, and how to use kind of the lower level compilation tools, although we abstract some of that away for you as well. So you're going to get used to this and you're going to have to use this, but it means that you don't have this debugger where you get to push a little running man and it runs your program, right? It doesn't happen anymore. So we're a little bit beyond that. But what I'm going to do is I'm actually going to create a little directory here, 107 class, and then cd into that. And what I'm going to do is I'm just going to we're just write a little program in an editor. Now my editor of choice is Vim. You guys can use Emacs or Sublime Text or some other editor, but I'm going to use this one for now. And we're just going to start writing. So if you remember your C++, you have pound includes. There are no more pound include IO stream. right? In C, we do it a little bit different. We have pound include stdio.h, and we generally include another one too, which is pound include stdlib.h. Okay, those are our pound includes. There's no more of this using namespace business. C doesn't have namespaces. All right, so let's just write our main function, much like we would in C. C++, very similar. Okay, now if we're going to do hello world, you might be going, oh, let's do cout. No more cout in C++ in C. We're down to another. We have another function called printf, and printf works the following way. It's actually It's actually a function, and you put in something like hello world, like that, and then you might say, okay, well maybe we then do like an end. No more endls, no more of that stuff. You actually have to embed this into the actual text itself, and \n is just a new line. Okay, and return 0, and that should do it. All right, there's our hello world program. Okay, that's that. Shouldn't look too different than your C++, but that's the way it goes. Okay, I'm going to save it. Now, again, no little running man or like green arrow to press. We actually have to compile this. In class, you will generally do this, make, and compile it. But I didn't create a make file for this. I'm going to show you what's happening underneath the hood a little bit in this. We're using a compiler called GCC, which stands for the GNU Compiler Collection. And we have to put some flags into there. And the flags, you'll see why these are needed a little bit later. And if you do assignment 0, you'll find out as well. But what we're going to do is we're going to make it so that the debugger works. One of the things you'll find in this class is you write lots of programs and then you go into the debugger and see what's wrong with them or what's right about them and so forth. So we're going to do that. We're also going to use what we call a standard GNU 99 and like that. Don't worry too much about the details here. But basically we're going to say compile hello.c, put it in an output file called hello, and if everything works right, you don't get any information, right? It just means, oh, it compiled and it worked fine. And there's a program called hello now, and if I just type hello, it says, oh, sorry, the hello program can't be found, right? What you need to do is you need to tell it, run the hello program that's in your current directory. And again, you're going to learn all this stuff later. Turns out your current directory is called dot. ./hello will tell you, run the hello program that's in your current directory, and there we go. Okay, we've written our hello world program. Okay, let's just modify it a little bit. Okay, I'm going to modify it a little bit. I'm going to put a little for loop in here. For I equals 0, I is less than 10. Let's see, I plus plus, and we're going to do this, and there we go. And now I'm going to actually have it print out hello world and then a number, right? And in this case, I'm going to have it print like this. This little %d means, hey, whatever comes in after the string here goes in that position. And I'm going to put comma I, and it's going to say basically use that as a parameter for this function, replace the %d with I. You will learn all this stuff as we go along. And I believe that should do it. I'm going to go compile it again, and there we go. And if we run it, there we go. Okay, that shouldn't have been too weird, right? That shouldn't have been too like weird as far as like what the program does, right? Now watch this. I'm going to launch into something that we're going to get to much later in the course and just show you a couple things. Okay, I'm in the GDB debugger. Like I'm running the debugger on the program right now, and if I type run, it will actually run the program and tell us all this other neat stuff about it, like it exited normally and it run and so forth. And I can actually look at the program. Okay, and we can actually put breakpoints in the program just like you would with any debugger. Okay. Another interesting thing we can do, and again, this is going to come halfway through the course when you actually see this stuff, is I can type disas main, and there's your program in assembly language. It's probably making your eyes bleed a little bit, right? That's your program. That's what the compiler turned your program into. In fact, it turned it into a bunch of binary code, but in the sense of this is what it's actually turning it into in terms of assembly language. There's some things up there now. Do I need you to know? Do we need to know anything about that right now? No, right? Hey, guess what? There's a call function in here. It says call the printf function. There's some other weird things in here like, what is this? Like all these like hexadecimal numbers, which we're going to learn a little bit later today or on Friday. I don't know, let's look at something. Let's look at what that 0x blah, blah, blah. I happen to know that's a memory address, okay? And it's going to hold something in there, right? And if we type, let's see, if we type x/10, 10BS and then 0X. What was it here? 4005F4. And it doesn't crash on me. There we go. Hey, look what's there. That's where our hello world lives, right? So we're going to learn about all this stuff, right? Right now, you don't need to worry about the... And by the way, it says you can't access the memory somewhere like down the line because we don't have access to that memory. But there's where our hello world lives, right there, right? Watch this. I could do this if I type... let's see. If I type x/10x and 0x4005F4, believe that's it. There's hello in what we call ASCII, which is also hexadecimal. 48, any idea what letter that is? Uppercase H. How do I know that? Well, I don't know. Let's go find out. Man ASCII. We're looking for 48. If you go down and you look at the manual, again, you will get all this in assignment 0. I'm just kind of previewing this. Notice up here, it says hex up here. Okay? If we look at hex down there and we go down to 48, that stands for H. Right? So there's all these little things that you're going to be able to learn. Now we're kind of getting underneath the hood here by saying, oh, here's what the hexadecimal code looks like for hello world. Those are the kinds of things we're going to see during this class. Okay? All right. So I think that was my little demo as far as that goes. We are back to more logistics. I don't know how you got stuck with all logistics here.
I know, I got all the logistics.
Okay.
Thank you. All right. What do I have left? Well, actually, some of this I already kind of got to you. Actually, I did my first round of logistics, so we were kind of breaking this up, right? The things we wanted to be sure you got to, we maybe did twice. That way we'll be sure that you catch up the first time or the second time, right? We're going to be meeting here, 1:30 to 2:50, and Monday, Friday, probably, right? The labs, as I said, will be these 2-hour sections on the Tuesday, Wednesday, Thursday. We're going to open the section sign-ups, the lab section sign-ups tomorrow morning at 10 a.m. It's kind of a first-come, first-served thing. We'll be able to get everybody probably in a place that'll work for them, but if you are highly constrained, for example, if you know there's just one of those times, because we basically have labs 10:30, 1:30, 3:30, and 7 p.m. Tuesday, Wednesday, Thursday, so all 4 times, all 3 days. But if you happen to know that only one of those is really optimal for your schedule, then you're going to want to kind of set an alarm to be ready to go to kind of make sure you get into that. Otherwise, if you're a little flexible, there'll be a place, it'll all work out, right? So get yourself into a good setting for that. And then we'll have exams, right, that will, we already told you about the dates on that to make sure that you have those things. Other things I want to say before I get to this, but let's back up one, was just I want to in general talk a little bit about, Chris alluded to it, and I feel like I should do you the favor of sort of continuing that, which is like, we know this class is pretty challenging, right? It's kind of intense, right? We've got a lot of great things we want to do with you, and we have really a lot of high hopes for all the things we can do together if you're kind of willing to kind of dig deep with us and get into this. We also know, though, that there are a lot of things, like as Chris was showing you, that are going to be kind of overwhelming and new and different, right? You haven't seen before, right? We don't expect that you know units. We don't expect that you've already, worked in C. We don't expect that you've seen assembly. So we're throwing a lot of it at you right now to kind of give you this preview, but realize we're going to get you there, right, step by step, right? We're going to be doing this, day in, day out in lecture and lab, and the assignments to kind of guide you through that. And so realize we're on your side, right? We're not, this isn't you against us, right? We're trying to beat you into submission here. We really want you to come along with us, because we think there's really empowerment to be had if you could work with us on getting those skills up. And so to that end, I want to be reinforcing the ways that we can help, right? So our website has a lot of materials, right? Chris spent weeks doing these fabulous set of little Unix videos that tell you about how does the directory structure work? How does GDB work? How do you compile a program? So if you are not as familiar with those things, and we expect that most of you are not, so don't think of this as remedial. We put this together for you so that you had a place to go to kind of get up to speed on these things and get comfortable with them. So he walks you through, he has the watching you do stuff and him talking it through. There's stuff that's written if that's easier for you than watching a video, whatever it takes to kind of get used to this first week. We really want you to be like, I'm getting ready to get comfortable in this environment, figure out how these things work. I'm going to ask questions when I don't understand it. So we have a forum up on the piazza, right, where you can ask and answer each other's questions, talk it over there, right? We're going to hold office hours like crazy throughout the week, right? We have you can send an email to me or Chris, or we actually have this kind of CS107 CS, which is kind of just get to anybody on the 107 staff who can help me, if you have something that you really need a kind of a private conversation to have about, go that way. Whatever it takes to kind of look like, get the help you need and get moving forward on the thing that you're trying to do, right? So kind of think of this as we're all on your side, right? We really want you to succeed, and we kind of have amassed a big set of stuff to kind of help kind of keep you on the right track and moving forward. But I wouldn't do it's fair for me to say it's going to take some doing on your part, right? Like I can't inject this into your brain by osmosis, right, while you sleep, right? But you're gonna if you can meet us halfway, we can do a lot together. So now we'll flip to the next slide. There's always something I want to do on the first day because I feel like I think it's good to kind of have a group airing of this, right? So hopefully, I'm thinking you came here with some excitement and some energy and some information. You've taken the 106s and you've had a great experience and you want to go further. You're thinking about CS as a major, maybe it's a minor, maybe you're a CS plus X, maybe it's just a hobby. You've probably heard some things about 107 from other people, right? From people in your dorm or your RA or whatever. So there's a word on the street. So what I want you to do is we're going to take a little break from listening to us talk for a while. I want to give you a couple minutes to reflect for yourself on what you're looking forward to. What brought you here today? What are you excited about? What are you hearing that actually kind of gets you going and you're looking forward to the journey ahead? And then also maybe a little bit of like, okay, is there something you need to air about a concern or a worry or a shady issue that you'd like to help do? So what you do, talk to your neighbors, talk to each other, tell each other what you've heard, tell each other what you think is fact and fiction and what's not. And then what we'll do is we'll try to bubble up some of that stuff after you get a chance to talk it over with your immediate community to try to get a good community feel about what we're looking forward to and what ways we can help make you feel comfortable and welcome in the kind of journey to come. So let me give you. I'm gonna set my watch for like 2 minutes of introduce yourself to your neighbors, say hello, tell them why you're here.
One question.
Yeah.
Can you say more than lab section?
We'll get there. We'll get back to it. Yeah, I got it. Countdown timer for 2 minutes.
It's on the lab slide, right? The one that it's like it's all pretty circular. Like you keep forgetting it's on some later slide, and then you want to tell them now, and then you get the slide, you're like, oh, I already said that.
There's no clock in here, is there?
No. There used to be one.
I brought a clock to one of the installed a clock in my one of the classroom, so I'm gonna go steal it.
Oh, did you?
I'll put it right back there or something.
Yeah.
Maybe on the class.
There used to be one. So I used to bring my phone as my go-to thing. But yeah, sometimes when you talk these things, it's like, I think I'm talking to each other. That's all I know. So, hello, that would be awesome. It's a fun together. It's tricky because you want to both say, you've got a lot of stuff to do. It's a good thing, but like, you don't know. Some mess.
You got 30 seconds left.
Oh, good. Look at you. How'd you do that?
Just say, you hold on the button and go, countdown time for 2 minutes. And he goes, okay.
Dude. Listen to me.
There it goes.
Everybody wants me. I'm very important. Okay, that was good. You guys have lots to say to each other. Let's hear it. Let's start with the good news. I need to hear good news. Good news, I'm all about the good news. Tell me something that you're pretty excited about. What are you hearing that kind of resonates a little bit with your group here?
I wanted to be a master of C.
You are going to be a master of C. I promise. You're going to be a wizard. You get to use all these cool words, right? This is the backstage pass of CS classes right here, right? Like the things that the nerds and the uber geeks and whatnot, right, have going on, you're going to have going on. So you that is the price of admission for 107 is just all this incredible, like, I get it, I understand it, I can make sense of it, I can analyze it, I can talk it through, I know why this program does this, that program does that. You, like, I'm telling you, cocktail party, sort of banter, you are the master. Like, no one can do it better than you. I taught my husband's an ME. He thinks he knows how to program, but he doesn't. And he knows how to do everything else, though. Like, he's superhuman, really. But it's funny, like, I taught him just enough, kind of like random things to go to parties with my friends and then try to slip in, he always tries to kind of use the same sort of schlock. It doesn't really work. I'm going to teach you guys way more than I'll ever teach him, so don't worry. What else is good? What else are we going to get out of this? It's going to be fun.
Just kind of like connecting my understanding of like the lower level working on the computer and the upper level that I've worked with.
Yeah, I think that's an extremely empowering way to not have to kind of guess about things or wonder or be mystified. Like I can totally remember this time I was working with a 105 student who had a program that behaved this way. You put a print statement in, you put a print statement out. So the print statement actually had this other effect than just the addition or subtraction of the print statement. And I remember when I realized what it was doing, I tried to explain to this poor 105 student why this was so awesome. And there I am in the classroom, like, look at this, and then the web memory, and I look at her just giving me this, like, whatever, right? Like, I'm just trying to get my program to work, crazy person, right? But I want you to be with me. I want you to be crazy. I want you to say, I really want to figure that out. I want to trace it out. I want to dig in. I want to look at it. I want to get to the bugger on that. And I'm going to, when I get done, I'm going to completely understand it, and that is going to totally rock. And what else is great? I want all the good news first, so I can take the bad news after that.
I'm excited for the classes in EE and CS107 Lecture.
Yeah. But once you get this, it really opens up this whole door of understanding computer architecture, right? Like what the sort of multi-core architecture, things that we're moving into. How do those things work? What do you need to know, right, from the software side to be able to kind of really appreciate that hardware? These are all good things. I'll tell you another secret about 107, not even the secret, which is for a lot of internships and research opportunities and employers, right, and recruitment situations, right, 107 actually kind of serves, and my team will validate with me, like, it's kind of the dividing line between you being, like, when they get the resumes, it's like they're dividing them into two piles, pre-107, post-107, right? Like, pre-107 students are great, they have certain goals for that, but once you get to 107, they're like, okay, you have just become a lot more interesting to us, right? We have much more faith in the kind of things that we can give to you and have you succeed at, and we're really excited to kind of take advantage of that knowledge that you have there. So it's kind of I wear that proudly. I think that's a really neat role for 107 to serve, right? Is to kind of be taking you from this one place and kind of just really leveling you up and creating this kind of powerful juju that you can use to do a lot of cool things. So I'm super into that. All right, let's hear a little bit of the things to be a little bit anxious or fearful about that I'm going to tell you don't be afraid of. Let's go.
Well, this is more just like a logistics question.
Yeah.
But, we have remote access to the Linux workstation.
You do. So there's actually like this cluster that's in BU08 that's called the NIST, right? But you can SSH your way in from anywhere. Your dorm room, over field, wherever you got some Wi-Fi, right? You're good. You're in Starbucks and you're at ultra caffeine.
Do it from an airplane.
Do it from an airplane. Well, that's true. Yeah, just you need network access of some sort, and it's actually on campus, off campus, the whole bit. It's definitely slower depending on the kind of speed of that pipe that you've got there. So if you want to work over 24 miles open or anything like that. All right, so let's go back to okay, is there something that I can ease your mind about? Tell you why it's going to be better than Earth. It's not as scary as you might have heard. There we go.
I didn't take 106 here. I did somewhere else. I did a job, so I've never seen C++.
Okay.
How's that different?
Okay, that's a great question, because there's actually a pretty big mix of now where we've been actually playing a little bit with our work to say it's D and so that the understanding of which language you have C and what your experience is in is actually kind of more murky than it's ever been, right, at this time and place, right? So our assumption is going to be not that you have great experience with C++, nor Java, nor JavaScript, or anything like that. We are really counting on though you being pretty comfortable with the kind of programming topics that are covered in the 106B in any language. So data abstraction, right, recursion, data structures like hash tables and vectors and things like that, how they're implemented, what the kind of so the language you're working in, they have expressed it syntactically very different, and they have different safety features and different trade-offs, right? We're all going to be kind of at ground zero when it comes to dealing with C. So, for example, one of the first things that we'll talk about, right, is how they represent strings, and the C strings are unlike any other language's strings. Every other language has a really reasonable, decent string package, and C does not, right? And so we're all going to be on this equal footing with like, feeling like, okay, we're having to deal with kind of this raw, arrangement of characters, right, and how that works out. So that, I think you're going to be in good company in terms of it being disorienting in some sense to move from whatever background you have into the C space. And so we're going to try to ease that transition by giving you kind of the right footing to get through the, okay, how do things work differently in C? And as Chris said, one of the really beautiful things about C, though, is C is very small. It's a very small language. It has a very small set of libraries. So what you need to get your head around is it's not that it's particularly easy, but it is at least constrained in this kind of like, okay, there are things I need to get my understanding and mastery of is actually kind of something I can get my head around, and not like C++ where it's just tentacles everywhere, right? All the interactions get a little crazy. Yes, thank you. What else? What else? Come on, tell me what you've really heard. I didn't hear the dirt. Here we go.
Since error checking should not in Java.
Yeah, so the whole idea of error checking and safety and kind of testing is actually going to become a kind of a new skill set for all of you. Because languages like Java or Python or a lot of these very safe and friendly languages, right, always have your back, right? They're looking out for you. You run off the end of an array, they're like, hey, you ran off the end of the array. C is more like, hey, you ran off in the array, you're going to get what you deserve. And so that's going to require kind of a new level of vigilance from you, because the symptom is going to just expose what the raw system is doing with that, right? And the raw system is generally just going to do the wrong thing, right? Like an undesirable thing. And we're going to see why it does those things. It's going to make perfect sense once you kind of see how the memory's laid out, that if you access off the end of the array, you actually hit the thing that's neighboring it. Well, what's neighboring it? You're going to learn what's neighboring it and why. But that doesn't make the behavior, all that easier the first time you see it to actually understand it. But when we get our head around it, we're going to really be able to connect up all those dots, and it's going to be really a very kind of empowering moment. But yeah, there's definitely going to be more on you and more. There's some frustration to that. I'll be the first to admit I love to code, and I love systems stuff. And I know Chris and our TAs are all in that same boat, and that makes us crazy nerdy. But I want you to come with me just for a quarter and just enjoy I can really get my head around this. I can really make sense of this. I'm not going to just sweep this under the rug. I'm not just going to move that around and kind of get the bug to go away. I'm going to figure out why the bug is going away, why this change has this effect, and kind of really build that together. I think that is just what 107 can really give to you, is this deep and connected understanding of all the moving parts, right? That is, I think, really transcends the C language and the systems environment, right, to just generally make you into a really strong and capable programmer of any language in any context. So, I would say we know that not all of you are kind of destined to be, let's say, systems people. You're not going to write the next generation operating system or compilers or developer tools, the kind of domain of systems people, right, is building all that infrastructure out for us, right? We do need a lot of people to do that, so if you're interested in it, we're all in favor of that becoming the love and light of your life. But many of you will go on to AI or theory or HDI, right? And then this deep understanding of the system is not going to be the thing that every day you draw upon your work. You're not going to be dropping down the assembly type level to look at your web page to see what's wrong, right? That's not going to be the way it happens. But I do think having this kind of foundational knowledge of what the system's capable of, how it reacts to these situations, what's fast, what's slow, right, will actually inform sort of better programming in any context, right? So think of it as actually kind of it's a little bit of it may be a extracurricular to the thing that's going to be your life's work, to have this exposure to systems, but I think it will actually still be very informative and useful in a broad array of contexts, so don't think of it as a dead end or something like that. Come on, there's got to be a little more fear. You guys have no fear?
What about heap allocator?
What about heap allocator? Oh. You should be afraid. Sorry, I take it back. No. So we do have time. We work ourselves up to a pretty significant kind of capstone at the end, which has been traditionally heap allocator. We really like that experience of the capstone at the end. So whether it's heap allocator or something like that, or some variant, we kind of play with it a lot to try different things out there. But we think it is really neat to be able to get to the end of 107 and kind of put all your knowledge together in one combined kind of fairly bigger project, bigger scale than the weekly assignments, and kind of so we usually need more time to work on that, right? And kind of more structure to kind of help you get through that. We think that's a really important part of the experience. So we're going to be making something like that work at the end. It is something to kind of have a little bit fun in terms of just scheduling. Like a lot of times, if you get you're one of those students who I was one of those students, so I can admit did this. Like, you know, who kind of think, yeah, I'm gonna catch up over Thanksgiving. I have a lot of reading and stuff I haven't really done, but it's all gonna come together at the last minute. Those kind of work habits sometimes get you in a little trouble when you have classes that are loaded back and loaded. So this class is largely kind of constant throughout the quarter, but that one project at the end is kind of a notch up. And so when thinking about your scheduling, not hunting too many things into the 90% week that will collide with it may serve you well. So maybe kind of having that in mind.
If I can mention one thing.
Yeah.
Yes, this is a difficult class. Nobody's saying this isn't a difficult class. But you guys are prepared. If you went through either 106A, 106B, 106X, or any of those, or at a different school, a data structure type class, you are well prepared to do well in 107. So don't think, oh, it's this big scary class. It's the next class. And yes, it's frustrating, and yes, there are frustrating parts to the assignments, and you're going to learn new things, but that's kind of the beauty of it. But you are prepared, so don't think, wow, this is like overwhelming. You're ready for it.
Here we go.
What's the policy on collaboration?
So we have a very similar policy that the department has adopted, right, which is, you know, when you're working on non-assignment things, so for the labs, for working the lecture material stuff, for the reading, like, absolutely, we're a whole, you know, like, all invested in this together, we're big learning communities on Piazzas or all those things. When it comes time, though, to write the assignments, we think that you're really going to build out your own skills by working individually. That many of them, you know, there's going to be some moment where you have a particular bug and whole thing where you're going to need some help. We're prepared to do that. We really want you to come to the staff because we actually know how to help you without kind of overly leading you. If you work together or you work with an older student, in the past we've had that kind of result in things we don't really like, which is somebody just saying, well, here's how I did it, right? And then the person's like, oh, well, then why would I write it myself when I have, here's how I did it? Like, what's the novelty in writing this for myself when I have a completely working version here? Or someone kind of just gets you past an issue that maybe there was a lot of learning that went into getting through that, but someone else may not know how to lead you to the state of understanding, but just knows how to give you an answer. So to that end, right, when it comes time to the things that are being turned in to be assessed for grading, which will be the exams, the assignments, right, the labs are participation based, so it's all you know, community and collaborative. We are going to ask that you're doing that work yourself and that you are acknowledging that you submitted, yeah, this is my work. This really represents my thinking, my coding, my debugging, right, and my understanding, right, it was developed through doing this. So that's really the important thing. It's not less to do with us wanting to keep you from helping each other. It's more like that the help sometimes ends up interfering with the learning. Sometimes we have done the final projects and the team projects, sometimes we don't, so I will say yes or no, and that'll happen this time. It kind of depends on what we think is going to work. So. All right, is that good? You look good. You look happy. I like happy. I like feeling good. I want us to be, you know, kind of on a journey we all want to be on together, right? And really kind of hope that you see that there's going to be a lot of value for it into you and what you invested and what you get out of it. I think it really kind of serve you well. So I'm glad to do it. I'm kind of looking forward to it. All right, go back to you, dude.
All right. So as Julie mentioned, and I mentioned earlier as well, the assignment 0 is how you're going to learn how to do Unix and learn how to do that terminal stuff. And also, it's going to be there for a reference for you as you go along to the course. So we're going to have a big old link right at the top on the menu bar. You can go back to look at the assignment. Now, it's actually not published yet because of the way the website worked and so forth with them updating. We're going to actually publish it tomorrow morning.
Yeah.
I guess we're going to publish it tomorrow morning. It's going to be due next Monday. But there's really no coding aspect to it. It's all about learning the tools that we're going to be using for that. So there's a few different parts to it. You're going to do all the Unix overview documents or videos. You're going to learn how to what we call clone the assignment, which is basically get the starter code. It's not a zip file anymore. You have to get it through this command that you type. And then there's some the questions you have to answer that's actually going to get submitted. You have to learn how to make an assignment, and you actually have to submit it. So not in the big picture, it's not that much. It's just there's a lot of things that you're going to have to kind of start to learn as you go along. So that's assignment 0, and you'll see that tomorrow morning. All right, lab sign up. So Julie mentioned this as well. There's a web page for lab signups here. That page takes you to a page that gives you an overview. There's a big sign up button, and if you click on it now, nothing will happen, or we'll go to a page that says it's not open yet. Tomorrow, at 10 a.m. We will open that up. Lab signups is first come, first serve. If you know that you have a particular time, can we see the lab times beforehand?
It's basically, 10:30, 1:30, 3:30,
10:30, 1:30, 3:30,
7 p.m.
7 p.m. on Wednesdays, Thursdays.
Tuesdays, Wednesdays.
Tuesdays, Wednesdays, Thursdays. Okay, there we go. All right. So anyway, if you know that you got a very particular time and your schedule's very rough, get on there tomorrow at 10 a.m. and sign up. All right. The labs themselves, as Julie said, they're collaborative. They're led by the TAs, and they're going to be a good opportunity for you to practice this stuff in an environment where you can ask lots of questions and work with a partner and so forth. Okay. So that was it for the logistical kind of things. So for the next, let's see, we're here till 2:50, right? Okay, so we've got 25 minutes or so to kind of get into some details about the first topic that we're going to talk about, which we're calling bits and bytes. And I want to start out talking, we're going to go way low right now, right? We're going to go way back. Okay, there's a 0, right? A 0 and a 1. You want to see that again? A 0 and a 1. Okay? Those are the 2 digits we use in binary arithmetic. Now, you guys may have used this before or learned how to convert bases and so forth, and you've probably always heard that computers are binary, right? Well, now we're going to start to learn about what that actually means in real life. Okay? What does it mean for a computer to be binary? Right? Why do we care about 1s and 0s, and what does that buy for us in this case? Well, it turns out that the way computers are built, they rely on this idea of being able to tell whether something is a 0 or a 1. And at the very bottommost level, it all gets built up from that starting point. Okay, we have lots of ways to do that in real life, clockwise or counterclockwise, 0 or 1. Right? A light bulb's off or on, 0 or 1. Right? Punch cards. These are kind of way back in the day, but the way these punch cards worked were you either had a hole, which was a 0, or you had a no hole, which meant that it was a 1. And those are different ways of representing 1s and 0s. Okay? And it turns out you can build up logic just from those basic parts. Right? Electronic computers are built using transistors, and somebody was talking about the difference between, or the tie-in with EE classes and CS classes. This is where it starts to get tied in. Like, if you love this stuff, go become a computer engineer. You're going to do this all day. But what transistors have a mode where you can either say it's either off or on. And using some Boolean logic from the very bottommost level, you can start to build up from the 1s and 0s until you can represent anything, as it turns out. So that's why we use 1s and 0s, because at the very heart of the computer, you've got all these transistors which are either on or off, and that's how they work. Okay, and that's how computers itself work. If you want to look up something interesting, look up the ternary computer, which is a base 3 computer that the Soviet Union produced in like the 70s. There's not too much information online about that, but it's kind of amazing. They actually decided, hey, we don't want to use just 0 or 1, we want to use 0, 1, or 2. So it was interesting. But our computers are all binary computers. Okay, so an on-off we call a bit. Okay, there's a lot of text on this slide. Sorry about that. On-off is called a bit. Okay, and having a bit, well, it's not particularly useful. You can only represent 2 things with 1 bit, right? Only two states. So what we can do is we can combine bits together to get more states. Okay, we all know about decimal notation, right? This is what we've been doing math in our entire lives. Okay, and the reason we have decimal is because we have 10 fingers, by the way. Okay, and that's the way that, well, the anthropologists will tell you that that's kind of probably how this all came about, was why we have base 10 instead of some other base. I kind of wish we had 12 fingers, because base 12 is a little bit better base, but probably be better base 16, but we'll get to that. We'd look a little different, whatever. But if we want to combine in base 10, if we want to build numbers greater than 1 digit, we just add another digit, right? So base 10 has these 10 digits, right? And we can represent up to 10 different numbers with 10 digits, right? 0, 2, 5, 6, 7, 8, 9, that's 10 numbers. That's as much as we can get. And then, of course, we know, if we want to access more numbers, we add another digit. Okay, so then we can get 10, 11, 12, etc. Well, binary is exactly the same way. Okay, binary is exactly the same way, except now there's only 2 digits. So you got to start over much earlier, right? We can represent 2 numbers with 0 or 1. If we want to represent more, we have to add a digit. So then we add a 3rd digit, and we can represent, now we can represent 0 or 1 or 1 0 or 1 1. Right? Now we've represented 4 different things. Okay, if we add another digit, we can represent even more. We'll get to some details about that later. But that's how you can start building up from those like basic 0 or 1. You just add more bits. That's what it goes to. Okay? Once you add more bits, you can end up creating any different numbers or representations of those numbers. Right? Your computer doesn't care about strings or characters or whatever. It just calls everything a number. And then we abstractly deal with this. Like, for instance, we come up with a code, the ASCII code, which I showed you a little bit earlier, if you remember, where we have a character representation, and we can look at the binary representation of that. So before we looked at uppercase H. Now, this happens to be the binary representation, 0, 1, 0, 0, 1, 0, 0, 0, of uppercase H in this code that humans created that is a representation in binary form of some abstract concept that the humans created. Okay, but the point is, we have binary bits, we can build them up and get any number. Beautiful. I think that's beautiful anyway. Okay, we're going to talk about 3 different types of number representations in this class. Okay, we're going to talk about, in general, we're going to talk about lots of different ways to represent numbers, but 3 big ones. We're going to talk about unsigned integers. Unsigned just means that there's no sign associated with that integer. An integer, obviously, not no decimal. But we've got unsigned integers, which are just, we're just going to consider them positive. Okay? 0, 1, 2, all the way up. Positive or 0. We've also got signed integers. That's going to be completely different. We're going to go over this over the next couple weeks. Okay, next two lectures, I guess. Signed integers are negative, positive, and 0. And these are the ones we're normally used to dealing with. You say int, that gives you a signed integer. So we're going to deal with those all the time. Then we're also going to have this idea of floating point numbers. Now, floating point numbers are a base 2 representation of scientific notation. Right? So it's now saying, oh, I don't want to just deal with integers anymore. I want to deal with numbers like 0.1 or 4.87563 times 10 to the 3rd, etc. Well, you have to do that using this binary notation because we already said that's all the computer knows. So some very clever people decided on various ways of representing numbers, one of which we call floating point representation, and we're going to do that. Doubles and floats are just floating point numbers, but in this class we get to find out how they're actually built. So that's kind of cool. Okay? Now, I want to write a little program. We already did a couple other programs, but I'm going to do another little program with you. How are we doing on time anyway? Good? Yeah, I just want to make sure we don't. Okay, so I'm going to do another program. In this case, I'm going to call this program multtest.c. Okay? Same thing as before, pound include IO, not IOstream, still in C106B mode. stdio.h and pound include stdlib.h. Okay? And int main. And let's do an integer, some integer math. Int a equals 200. Int b equals, not the word b, equals 300. Int c equals 400. Int d equals 500. Okay. And then how about this? Int answer equals a times b times c times d, like that. And then let's print it out. Printf. Now, we showed this a little bit earlier. Printf %d says print the decimal value that comes before, and then a new line, that comes after. New line, and then answer, like that. And then, of course, we want to do return 0, and like that. Everything look okay? Is it std lib? Yeah. Okay. And, oops. There we go. Okay. So let's compile this like we did before. gcc-g-o0 std equals GNU 99. You will not have to worry about all these details. In fact, I should have just made makefiles for all these things. But that's it. And we're going to do multtest.c, multtest, like that. And, oops. Is it not getting, oh, forgot the dash. There we go, dash, there we go, there we go. Okay, compiled just fine. And if we run it, let's see what happens. All right. 200 times 300 times 400 times 500 equals negative 884,901,888. That's a problem. I think it's a problem anyway. Here's the deal. We did this. We came up with this number, right? And we had an issue, right? We came up with that number, and that's the issue. Well, what's going on here? Right? We call that an overflow, it turns out. Okay, here's what's going on. Remember in base 10, we said that you can represent 10 numbers with 1 digit, and 100 numbers with 2 digits, and 1,000 numbers with 3 digits, right? 0 to 999. In base 2, we can do the same exact thing. We talked about that already. You can represent 2 numbers with 0 to 1. You get 4 numbers with 0 to 1, 1. 0, 0, 1, 1. You get 8 numbers with 0, 0, 0 to 1, 1, 1. In other words, if you want to represent, or if you have n digits in base 10, you can represent up to 10 to the n numbers. That kind of makes sense once you think about it, right? In base 2, it's true that if you have n digits, you can now represent up to 2 to the n numbers. Well, guess what? Int is a 32-bit number, meaning you get 32 ones and zeros in a row, and that's how many numbers you can represent, meaning you can represent 2 to the 32 different numbers with an int. Right? 2 to the 32 is 4,294,967,296. 200 times 300 times 400 times 500? 12 billion. Do we have a problem? Yes, we have a problem, right? This is why we can't do this. Because that number is too big for the number that we've tried to stick the answer into. Right? We've said, look, it's not working out. If you went and did this in Python, Python has some other interesting things going on where it allows you to do integers as big as you want. Right? You can do integers as big as you want, but C does not do that, at least not the main data types. Neither did C++, by the way. You might have found the exact same problem. But that's what's happening there. Okay? So it's even worse than that, as it turns out. As it turns out, the integers are actually signed, as we said before, right? Meaning that you get half of them are negative and half of them are positive. So you only get half of those 2 to 32. It turns out there's a -1. We'll learn about why that's the case in the next lecture. But you get 2 billion plus change number of positive integers. So you're still, you're not going to represent all 12. You're not going to represent 12 billion. So we've got to do something a little bit different when we deal with our numbers. Okay? So that's one of the things we're going to have to worry about when we get into here. Now, here's the good news. The good news is that no matter how we actually do this arithmetic on integers like this, right? 500, 400, 300, 200, et cetera, et cetera, et cetera, no matter how we do this, they're all going to give us the same wrong answer. Now, you say, well, why is that a good thing? Well, let me show you a slightly different program. Okay? Let's look at this program. In fact, given the time, I'll just show you this program instead of typing it into the computer. Here's the program. This program is a little bit different. It uses floats, right? Now, I'll tell you, floats are actually 32-bit floating point numbers. They still use 32 bits, right? But they're coded in such a way that you get a huge range of digits to use, okay? There's some nuances there, too. And in fact, this is going to come up in a few weeks in class. But here's the program, and normally we kind of use doubles in class. The same sort of thing would happen to doubles as well, as it turns out. But in this case, okay, we're going to have float A, 3.14. Great. Float B, 1 times 10 to the 20th. That's how you represent 1 times 10 to the 20th. Turns out. And we're going to print two things out. We're going to print out 3.14 plus 1 times 10 to the 20th. Minus 1 times 10 to the 20th. All right? And then we're also going to print out 3.14 plus the quantity 1 times 10 to the 20th minus 1 times 10 to the 20th. Now, anybody who's done grade school arithmetic would know that this should print out what? 3.14, right? I mean, you're 3.14. You are just doing this kind of cancels itself out, right? Well, when we run this, we compile it, and then we run it, and this comes out. This one prints out 0, and this one prints out the actual correct mathematical number, which is 3.14, which means we did the same thing in a different order and got garbage. That is a little bit more scary, right? Because now we've got an issue of, we're now dealing with the fact that we've got a bigger problem here, where we have an issue where now not only do we have something going wrong that we might be able to figure out, now we've got something going wrong that's just doing it by reordering things, right? Associativity and commutativity and all that comes into play. So we've got kind of a problem there. So we will get to that in a couple weeks about how these numbers are represented. But suffice to say that when you're dealing with a limited number of bits, you have to worry about your number representation. You can't represent any number known to man by just those number of bits. That reminds me of a funny story. When I have nephews. One's 2 nephews, 9 and 7. And this was a couple years ago when the youngest was 5 years old. I was in the car with him and I was just trying to make conversation. I said, "Hey, what's the biggest number?" And my nephew said, he thought a lot about it. 100. And I said, oh, what about 101? And he said, and he thought over the morning and goes, 1,000. I said, what about 1,001? You can see his brain like exploding. And then my oldest nephew goes, it's infinity. And I said, infinity's not a number, go away. But anyway, the point is that we do have a maximum number here, right? You might have used it in 106B. We've got this int max and float max and all that. Numbers that are capped because of the number of digits that we're allowed to use in our integers. So that's one thing we have to worry about. Okay? Both C and C++ have specific representations that allow for these sorts of things, right? When you do your math, the compiler is not going to check it, and the runtime is not going to check it. In Java, you actually crash the program when these things happen, generally, right? When you do something like that in Java, it goes, I'm sorry, you overflowed, we're going to crash the program because you need to worry about that. That's unsafe. Why is it unsafe? Well, if something happens in your program that keeps the program going but is undefined, or defined in some way you didn't expect, then you've got potential for somebody who's nefarious to come in and actually ruin your day. So C++ and C doesn't allow for, or doesn't do those extra special checks for you. Okay, so those are the basic numbers. Let's take a couple more minutes, we've got 5 more minutes, to talk really briefly about information storage. Okay? We're now trying to take these numbers, we're trying to actually store them somehow. Okay, in our computer. Now, what does that mean? Well, everything in C can be thought of as bits, like we've talked about, but not in the same sense of here's a bit, and then here's another bit, and here's another bit. We actually chunk things up. We chunk things up into a block of 8 bits, which we call a byte. Okay, and you guys have probably heard this before, but now you're going to get into what does this actually mean, and where does it come from? Well, the reasons we do this, I guess you'll have to go to the electrical engineering department to find out more about that. The reason we chunk this into bytes is kind of a lower level idea. But the big picture is you can only address things in bytes. You can't say, I want the 482nd bit of something. You have to say, how many bytes is that, and then look at that particular byte. And it goes to efficiency and so forth. But this should look somewhat familiar from 106B, right? When you look at bytes on a bit-by, we're going to look at bytes on a bit-by-bit level eventually. But in a computer system, you've got memory, which is just a big, long array, right? Memory is just a big, long array of addresses where each address refers to the next byte along those arrays. It's not the next bit, it's the next byte. So just start thinking about that and realize that we can actually represent these. Now, this is actually a little bit wrong because if you're going to go into this level, I think I grabbed this from my 106B slide. These should be each individual byte here, and some of these, actually, they would all fit into one byte. But the point is that each address, the next byte over, is what we're going to worry about. Now, remember, an address in C is just a pointer, right? So we're going to have pointers that will access particular bytes of memory. Okay. Each address address 0 is one byte, and 1 is the next byte, and so forth. Again, can't address a bit. You have to address these things at byte level. We'll get into more details about that as we go along. But let's talk about bytes a little bit more in a little bit more detail. Okay? 8 bits make up a byte. Therefore, we can represent numbers from 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1. Right? With, did I have one? Am I missing one there? 1, 2, 3, 4, 5, 6. I think I'm missing. I think. I think I'm missing one there. Should be 8 of them there. Okay? The range is, we already said it was like 2 to the number of bits, right? 2 to the 8th is 256. We can represent 256 different numbers with 1 byte. Okay? Now, it turns out that neither binary nor decimal are particularly good or convenient to write out these bytes. Right? Binary is too long. Okay? Binary digits, because you only have 2 digits, you have to write any decent number. You have a zillion digits, right? So that's not the best way to do it. Decimal is weird because it just does, things don't fit right. Like 8 isn't divisible in 10 and so forth. Right? So instead, we use a different base, which we're going to use base 16, which, while also being a power of 2, makes it very easy to do some conversions here. Okay, so when you notice I did the little demo at the beginning of class, I showed you some of the GDB, and I did this weird 0x digits. That was a hexadecimal number, as it turns out. Okay, so we're going to use hex, base 16, so let's talk about what that means for a minute. Okay, binary has digits 0 to 1. Decimal has digits 0 through 9. Hexadecimal has 16 digits, with base 16, yet we only have, in our language, 10 digits. So we have to add more digits. What do? We have the digits A, B, C, D, E, and F. And you're saying, those are letters and not digits. Well, now they're digits. Now they're digits, like in our case here, okay? And here's what they represent. Okay, the 0 through 9 are exactly the same as far as the base 16 goes. Then you get A, B, C, D. Well, A, because it's the next digit after 9, is represented by 10 in decimal. B is 11, C is 12, D is 13, E is 14, and F is 15. 16 digits, base 16, right? Well, if you look at the binary values here now, we didn't spend the time to talk about how you do calculations in binary quite yet, but the binary representations, 0, 1, and then you have to do 1, 0 is 2, and 1, 1 is 3, and then you have to go up another digit, so 1, 0, 0 is 4, etc. Okay? If you think about how that works in terms of the base, it makes sense, right? But as you go up here, you go to A is now 1, 0, 1, 0, B is 1, 0, 1, 1, and so forth. Okay? It makes it really easy to convert between base 2 and base 16 because you've got this nice, easy representation here. As long as you memorize some of these, or you just figure them out, it's actually very easy to do the conversion because it's 4 bits become 1 hexadecimal digit. Okay, so it's actually kind of nice. All right? The easiest thing to do, I think, is, this is what your book says too, memorize A. 10 is just 1, 0, 1, 0. 2 tens. That's an easy one, right? Memorize C, which is 1, 1, 0, 0, also not 2, 1, and then F, which is just all 1s. Memorize those 3, and then the other ones you can just figure out. It's either 1 more or 1 less, and it's easy to figure out. So you memorize those extras, you can figure out the other ones pretty easily. You should, and you will, memorize this chart here pretty quickly because you're going to use it so often. Okay? Well, let's do a little quick conversion. To convert this number, by the way, this little 0x represents hexadecimal. If you type 0x and then some number that can have letters A through F or numbers in them, that means it's a hexadecimal number. Okay? And if we convert that to binary, it's really easy to do, especially if you know this chart. You go to each digit over here, you look it up on the chart, and you write it down. Right? So the 1 is going to be what? It's going to be 0, 0, 0, 1. And then the 7 is going to be 0, 1, 1, 1. And then the 3 is going to be 0, 0, 1, 1, etc. See how that works? Not too hard. You know the chart, that's it. You've got those there. That's the one we just did. And then that becomes this nice long number. Notice something. That number is shorter than this number, significantly, right? And it's not like we can just sit here and memorize these numbers, but this number is much, much shorter than this whole big long number here, which is kind of the point. Okay? We would rather represent numbers in a nice, tidy package than trying to do all these zeros and ones, because you get lost really easily with zeros and ones. Okay? That's how converting into binary from hexadecimal. Each digit, go to our chart, which we'll memorize, and go. Okay? Questions on that? Not too bad. Maybe you've seen that before in other places. Okay, and then let's do converting this to hexadecimal. This one you have to do a little bit differently. You can't just start and grab the first 4, next 4, next 4, next 4. It doesn't work that way. You have to start from this side and look that up in the table. 0, 0, 1, 1 happens to be 3, right? So the last digit here is going to be 3. And then you go to the next one, you go 1, 0, 1, 1. You look that up and it goes 1, 0, 1, 1 is 11, right? And so it's B. and you look that up. And you do that each time, and you go back, and then the last one may or may not be all 4 digits. And you look that one up to 0011, and you look that's the 3, right? So you start from the right here to do this. Okay, it kind of goes like this. You go that one, then 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 that one, and that's and then that's that. Okay? All right. How are we doing on time? 1 more minute?
We're done.
We're done? Okay, I'll start here on Friday. See you guys then.
See you then. You got the long drill.
What's it?
You got the long drill.
Yeah, we did. Actually, it's fun.
I don't know for sure. I know there's a TikTok one that's
That'll work.
that is a custom cut down, so.
But that sounds like
Well, yeah, but I'll say this is this. So anything that's on the TikTok, I can